Indeed, and fascinating chat there from the decarbonisation team and Stuart. So thank you all again. Just to reiterate Stuart's thanks. Really good presentations, and I think today for most of us that have been listening to the day, I think you're getting a bit of a flavour now for what the activity that we're doing down here in Grimsby is aiming for. It is very different in lots of areas to where the Catapult have been. If you are aware of our operation up in Blythe and where we traditionally get involved. So it is a bit of a sea change for us, but very exciting. And I think that the team down here are very much looking forward for the next couple of years and how things start to progress. Okay, so this section is around the digital and data side of the business, and I think digital and data is one of those areas where it's pervasive into everything that we do in relation to the Catapult. So again, everything that you've heard about today, I mean, there is an element of digital and data sort of focused around there. And we've got three excellent speakers today. We're lucky to have Ty Burridge-Oakland from Cognitive Business, who I'll introduce properly in a minute. I've also got Jeremy Plester. Jeremy and I worked together a few years back in the days of Meteo Group, and Jeremy now is the commercial lead at MetDesk. And that's looking at weather forecasting for where we're going to be in the next 50 years. And again, that's has a direct impact on everything you do in relation to wind energy on the basis of the resource. And then finally, and by no means least, and Joshua is very much a key component working for Onyx Insight in relation to machine learning and artificial intelligence. And again, one of these key areas where the sector is starting to wake up to that potential and how things can start to move forward. Okay, so without further ado, we'll move quickly forward. I've not done a presentation because I think anything in the afternoon shift in my book means that we're looking for some punchy communication. So I'm not going to do the ORE Catapult sales pitch. You've probably had enough of that today. So this is more about the innovation and the people that sit behind it. So from Cognitive Business, I'd like to introduce Ty Burridge-Oakland, and Ty's has got 10 years experience in the energy sector. He's an undisputed tech leader, as he's told me on several occasions, with a formidable track record. And anybody that comes up with those lines as part of their bio, trust me, has got something to say. But he does back it up on the basis that he's got 4 patents across various territories, and he's led the creation of products worth over 200 million. So he has to have some degree of respect there. So I'll hand over to Ty, and with a focus on data maturity and the elements within machine learning and AI. Ty. I think we're good to go.
Okay, so I'm guessing that you guys are going to have to control this for me, unless you can give me access to.
Yeah, if you just give Vicky a prompt every time you need to change, we'll go from there.
Okay, great stuff. All right, sorry everybody for the slow technical start there. So my name's Ty. I am Managing Director at Cognitive Business. We are a powered by Catapult company, so very fortunate to be in that position. If we can go down, Vicky, by a slide. So what's Cognitive? Well, Cognitive was founded by a team of guys that came out of E.ON and subsequently Uniper when the company split in two. We created the advanced pattern recognition solution known as Spherical, which is a machine learning solution that operates globally across the Uniper fleet of conventional assets, but also includes modeling for wind turbines, offshore wind and onshore wind. At the peak, I think that was operating around 10,000 machine learning models every 5 to 10 minutes. The other aspect of the work that I think everyone's very interested in the moment of machine learning pattern recognition with regards to predictive maintenance, but once you've solved that or looked at that in a lot of detail, the next thing you start building into is this asset performance management, or APM, maintenance optimization area, which is the combination of all of these things together. And we were fortunate enough whilst at Uniper to basically invent and build out all of their technology in that area, including some really incredible reliability and maintenance optimization solutions that showed, as Steve said, a significant amount of value. So when you start seeing how all these things can fit together and really drive action, that's where it all starts to make sense. I think a lot of time and money gets put into data, but when you start driving action out of data, which is what this presentation is all about, that's where you really start understanding what it is that you're doing and where you're trying to get to. As Cognitive, we took a sidestep, I would suggest, and we've gone down the route of inventing some more technology that solve very specific problems. So we are working with RWE currently on a performance analysis, performance monitoring tool, where we're aiming to achieve very, very low errors, which enables operational performance analysis, as well as long-term performance analysis capable of seeing down to, as it says there, less than 1%, which we expect to be able to show us things, very early detection of operational problems, as I said, maybe your misalignment, pitch misalignment, and potentially blade erosion, leading edge blade erosion, that sort of thing. So we can really get into the real depths of data using AI and some physics, basically. We tend to work in partnership with the larger utilities, and our kind of real abilities lie within science engineering and data science, rather than just being a data science company, as well as being able to bring that together within software to solve problems that often are existing, that people know about, but are very, very difficult to get to the bottom of. So for instance, performance analysis, people have been doing performance analysis for years and years and years. But the errors that are associated with performance analysis are still very, very high unless you use specialist equipment such as LiDAR. Okay, Vicky, can we go to the next slide, please? So just a quick case study before I get on to data maturity. I think this might be useful for anyone who was just on the previous call as well. One of the things that we've got involved in as part of the kind of asset performance management aspect of offshore wind is looking at accessibility, offshore accessibility, whereby the current metrics that are used for accessibility, such as significant wave height, really are indicative but aren't the full story of the problem for whether or not you can make a crew transfer from a crew transfer vessel onto a turbine. This causes operators significant headaches with their planning, and often are behind on their maintenance activities because they can't plan easily or have a decent forecast going forward week by week. We took a slightly different approach, and this is coming back to our scientific and data science backgrounds. As a company, we work with the Offshore Wind Growth Partnership to put together a solution that's currently operating with an accuracy of about 97%, which uses some very high-tech ocean modeling in combination with real operational observation to determine whether or not crew transfers can take place at on a real operational wind farm. This isn't just offline data. Those sorts of problems, this sort of problem is quite difficult, and we use a combination of deep learning and scientific analysis to kind of bring together this kind of observed data with complex modeling data. This is an example, I suppose, of where you can't just rely on your data, but you have to rely on your scientific and engineering capacity and capability within your companies or from external companies like ours to support you to really get to the answers that are pretty tricky to get to. People have been operating with the significant wave height concept for a long time, and to be able to increase the accuracy, I think we were seeing accuracies of around 80% using that metric, to approaching 100%. So it says they're 97, but this is an AI solution. Therefore, it gets smarter over time to really drive asset optimization, asset performance management. You know, these things are the next tier of data and machine learning. We can knock on to the next one, please, Vicky. So operational data maturity, and the next slide, please, Vicky. These are quite quick. So we've worked with a number of companies across multiple industries, and every time we work with a new company, we noticed that actually there were lots of little idiosyncrasies around those companies and where they had sort of ideas of where they wanted to get to, but there was a developing trend in how they were getting there or failing to get there. So if we can go to the next one, please, Vicky. So we surveyed 61 industrial companies across 8 countries. This was a mixture of conventional power, wind, onshore, offshore, gas, manufactured oil and gas. And we found that there was a repeated truth across all of those companies. Next slide, please, Vicky. One thing is, as I said, that a lot of companies expect that they will embed AI within their operational solutions within the next 5 years, at least. You know, a lot of companies are really striving towards that right now. But when you start looking at how they're going to get there or what their fundamentals are, you realize that there are some key problems. Okay, next slide, please, Vicky. Please, Vicky. So a lot of companies, they don't actually have data in an AI ready state. So you might be collecting data. However, getting it ready for machine learning or AI isn't as simple as just collecting it. And a number of companies, although they are spending a lot of money on data and concepts around data, the fundamentals for their businesses require significant transformation. Next slide, please, Vicky. So the data maturity assessment that we created was a study just to get people to a point where they could realize where they are, where they truly are on the data maturity kind of funnel, I guess, and get there quickly. So we created a very short assessment. It takes about 5 to 10 minutes to complete, to give you a dip check, which we can subsequently build on and provide recommendations for as to where to go next. Okay, next slide, please, Vicky. One of the things that I think everybody believes, or a number of companies believe, and this really is different at different tiers within organizations, is that they are operating. So certainly at the higher tiers, the more asset management side of the businesses operate or believe they're operating at a high level, intelligence age, information age. So these are the names that we've given to the 4 different categories of data maturity. So intelligence and information age are really quite cutting edge. Intelligence age being that you're basically breaking down boundaries and really moving forwards with what you're doing with data and artificial intelligence, whereas the information age is using the kind of most up-to-date, off-the-shelf opportunities. And I think that when you look across an organization, you see quite a difference of opinion at the more operational front end of the coalface, as it were. Next slide, please, Vicky. And this was the truth. So when you break it down and realize where and how you need to use data, most companies, in fact, nearly every company, finds that it's operating in the dark age or the industrial age, which are the 2 other categories that we've created for this. So really not having that facility to drive action from their data in the way that they think they can. Okay, next slide, please. Which leads to a really interesting position, because basically to meet the goals of most of the operators' business plans, there are some steps that need to be taken right now. Otherwise, the improvements and expectation of integrating AI and machine learning just will not be realized. Next slide, please, Vicky. So here's the overview of the assessment. Category 1, 2, 3, and 4 are dark age, industrial age, information age, and intelligence age. And the concept really is that at the dark age, your focus is on acquisition. There's a lot of effort goes into just collecting data, and that causes a major problem with data. If you can't acquire it easily and you spend a lot of time acquiring it, you can't actually drive as much action as you should be able to out of it, because your budgets can very quickly be burnt up just on the acquisition. As you move through to the kind of intelligence age, this level 4, all of your acquisition is automated. Nearly all of your acquisition is automated. Very, very low requirement on acquisition, which means that you can do more action, more analysis, and drive action within an automated process, rather than having to analyze the data yourself as you would do in stages 2 and 3, which means that you can really focus on a different tier of the business, a different level of problem. The problems that people really want to focus on, which is around risk mitigation and optimization, rather than dealing with the fundamental engineering style levels of analysis, which as I think a lot of us know, can be dealt with automatically if you have your data in the right pipelines. So that really is where this concept of data maturity is trying to take people. So from this kind of dark age where everything is built around acquisition, you know, we have a lot of guys still going out with pen and paper, collecting information, translating that information to other systems, which means that the analysis of that data is very, very difficult, all the way through to having things that are live connected, live pipelines of data, which are being analyzed automatically by machine learning. And I think Josh will talk a bit more about how that can be done later. Okay, next slide, please, Vicky. Okay, so here's a breakdown of the different companies. I apologize for the difficulty in reading this, but we surveyed companies across power generation, renewables, oil and gas, energy networks, water manufacturing, and others. And you can see there the breakdown was around renewables and power generation with the highest number of companies with energy networks. Okay, next slide, please, Vicky. And this was the kind of outcome. So this somewhere between 1 and 2, we see a large distribution. So that's the dark age and industrial age of where most people are operating. There are some companies that are pushing the boundaries and operating towards the information age, with very few companies having any real steps into an intelligence age type business. So what does that really mean? Well, in terms of the breakdown, 64% of companies saw that their data was still in silos. They couldn't access their data across the organization. And 45% of companies believed that they were having very inconsistent data capture, which obviously, coming back to our maturity model previously, that has a knock-on impact to the way that you analyze data. If things are inconsistent, you spend much more time cleaning data just to do the analysis before you even drive action. Whereas the companies who are pushing the boundaries, which were about 12%, were gaining insight as pre-sight. So actually seeing issues developing automatically and having their automation, AI, machine learning, whatever you want to call it, built in to their data pipeline. Okay, thanks, Vicky. And this is a key step. POC is proof of concept for anybody who doesn't know. And for the majority of my career, I've seen lots of proof of concepts. Everybody focuses on delivering a proof of concept that shows value, but to get beyond proof of concept is a really big step. In fact, there's a bit of a gap, and that gap is data maturity. So to get to a point where you're actually delivering value in some kind of automatic way is huge. You know, it really is, and it does take a proper push from businesses, companies, you know, what across the patches, whether that be, as we've said, power generation, renewable, oil and gas. You know, that step has to be taken in data maturity. It also enables you to run more proof of concepts and get more value out of what you're already collecting if your maturity levels are higher. Okay, next slide, please, Vicky. And this is key, and this comes back to my first point. Cognitive are not a data science company. We are an engineering science, data science and software company combined. The requirement to really understand what it is that you can get out of your operational data is not something that your IT guys actually know. You know, it is a combination of those guys with your engineers, with your scientists, with your asset management teams, with your, you know, risk analysis teams to build a pipeline that's mature enough to be able to present information for all of those purposes. And that's when you can start taking this step into a really intelligent, automated asset performance management solution. And that's it, I think. One more slide, I think, Vicky. There we go, that's me. If you fancy contacting me or connecting with me, that QR code there is, just scan it on your phone, it'll take you into my LinkedIn and just say connect, and we can have a direct conversation.
That's been great, Ty. Thank you for that. And I think really a good insight as to, you know, where our sector needs to be from the point of view of a data maturity profile. And it's something that I think we at the Catapult take very seriously. And through programs like the Wind Digital Innovation Forum, which we run, where we try and pull together sort of the solution providers and the asset owners to push that boundary with regards to using AI and machine learning much more effectively. Do you have a couple of questions for you, Ty? One from Perizan from OMCE Insight, talking about your blade fault detection. He was asked about the data type. So is it acoustic or SCADA you use for that?
We are, at the moment, we're using SCADA data. The verification process for the blade inspections will be manual, and this is interesting because it comes back to what we were just talking about there. I think there's a lot of companies out there who are using AI as well to analyze blade data, bringing those things together, as well as the SCADA data that can show these deviations will be the next stage in the automation of that process.
Good. And I'm getting one or two questions coming through as well, just about, you know, what's the cognitive business's view on how machine learning can integrate more effectively with O&M and the wider context and balance of plant, for example, of that area?
Yeah, it's a tricky but very good problem. I think the reality is that predictive maintenance for certain assets is a reliability and therefore probability based problem. Very few assets that we ever work with within, you know, wind or power generation have a nice straight wear out curve. Bringing these things together with the right type of machine learning, and that's really key. You know, it isn't just there is a hammer called machine learning and use it to hit everything. You really have to pick the right tools and then connect them in the right way to form basically an intelligence layer within an organization that combines things like asset risk with predictive insights that you can generate from machine learning. And I think we're really lucky to have Josh on the call, who will subsequently be talking about how that actually works, which is really good. It means I don't have to do it, so that's really good. He's going to go into some good depth in that, so I think we can say that for Josh.
And just on the predictive maintenance side, a good question which is coming through for very old wind farms that have been installed from the 1990s, whose, let's be honest, the data sets are not designed for AI and machine learning, but could actually benefit in a lot of ways. What advice would you give to those owner operators?
I think you always have to balance your opportunity with your cost and your risk. In reality, there's no point in spending lots and lots of money on a new data pipeline or new data pipelines, installing lots of equipment, if the opportunity for making more money isn't really there. So it really is a tricky balance, but that's part of being an operational business. You really have to look at where that opportunity is, and we can certainly help you with that. You need to talk to, whether it's Cognitive or any other company. People tend to have the experience now. We've been operating wind for a long time, offshore wind for a little less time, but conventional power for a long time, and the principles do roll over from one asset type to another. Although the technology may seem different on the surface, the engineering and scientific principles underneath and asset management practices in reality underneath are the same.
That's good. And from my point, I appreciate we're pushing on time here, which is good. What are you guys working on at the moment? I know there's some things you can share and there's others you can't. So any sort of exciting areas that you're involved with?
Yeah, so I think that the biggest and most exciting area really is, as we touched on at the beginning, which is the performance analysis with RWE. I think that really is a game changer from the perspective of the way the performance analysis is done at the moment, to being able to see, in effect, 9% earlier. I know that sounds crazy in terms of, it's just numbers, but what that really means is that using a power curve, using anemometer style data to identify performance losses is a really, it's full of errors, that sort of problem. And you can do lots of things to slightly improve it, but what we're doing is taking an order of magnitude jump to be able to identify things earlier, and the amount of risk that mitigates and the savings that are possible at the moment does seem to be absolutely huge. The project around vessel accessibility for crew turbine transfers as well is actually making a real difference right now. We're literally using it this week. One of our directors is out working with our proof of concept wind farm, and they've already gleaned value from that now through deployment of that solution. So for me, what really excites me is driving action, and I feel that we are really pushing the boundaries in these areas.
Yeah, no, that sounds very exciting. A couple of more questions before we move on to our next speaker. So has the data shown to improve uptime, yield, and does it allow for bespoke servicing based on predictive modelling? That's a tough question to answer, I thought.
Just say that once more, Steve.
Yeah, has the data shown to improve uptime / yield, and does it allow for bespoke servicing based on predictive modelling?
Yes. I think the pattern of your maintenance schedule, policy, whatever you want to call it, is totally up for grabs especially with offshore wind. There's a lot of things that are run on a reactive schedule, and therefore being able to see things early before they create problems, especially with the weather conditions that you tend to see in offshore wind, being able to have a predictive capability can save a significant amount of money. One of the things that we did pre-cognitive was we defined a method for looking at tower frequency resonance to look at foundation degradation, and we were able to spot about 18 months out when certain wind turbines were actually going to basically fail. They weren't going to be operational anymore, which gave like an 18-month forward planning capability for the site where they can literally change what they were doing around those turbines. It really does have a big impact. But that is those little key insights are really hard to get to, and you need to really combine, as I said, the science and engineering with the data to get there. And it can be bespoke. It can be that certain sites have certain types of problems, and other sites just do not have those same problems.
Yeah,
and that crosses over from your equipment types as well. Vestas turbines have issues that potentially Siemens turbines don't. But these are all part and parcel of the industry.
Yeah, indeed. Fascinating stuff, and the sort of subject again. I think we could probably do a whole day just on AI and predictive maintenance and that whole maturity point, within the sector. And maybe that's something we'll consider as we go forward. I think again, just for where we sit from the OMCE's perspective, we do want to make sort of a regular themed position as we go through the year. And I'd like to definitely sort of pick up the whole AI/ML sort of discussion point that when we're back to some degree of normality, and we can meet up in a normal way, where we're using the facilities up in Grimsby to demonstrate a lot of this technology and thinking, as much as it's a good chat on this call. So thank you, Ty, for that. A really interesting insight from your perspective. Please stick around, because we've got a bit of a Q&A at the end of this session with all the speakers, very much like Stuart did, and Dan, so that again, if there's questions which come up through the chat, you can come back to the next one. So my next speaker, Jeremy Plester. Jeremy, as the mentioned before, commercial lead for MetDesk Limited. 20 years, first of all, as a meteorologist, so he actually sat on the desk and did charts, etc., for weather prediction. But now very much involved with the developing products and services for the energy market, for trading, power forecasting, O&M grid balancing, etc. So a real good depth and understanding of the sector. He's very much a key part of the MetDesk team, and it's really his job is there to simplify what are quite complex data sets into easy digestible weather information for us to use and understand. And if you think about it, the whole point of weather forecasting and getting to a point whereby it's a trusted sort of source of understanding from the sector has become even more important. I think the European weather forecasting is pretty good at the best of times, but as Jeremy's presentation will indicate, there's definitely some room for improvement. So Jeremy, welcome, and over to you.
Thanks, Steve. Yeah, so as Steve said, I'm Jeremy Plester. I work for a company called MetDesk. Now I'm just going to attempt to share my screen. There we go. Okay, yeah, so yeah, I work for a company called MetDesk. Hopefully everyone can see my slides right now. Steve, can you just confirm you can see everything there?
Yeah, all good, Jeremy.
Okay, good stuff. Yeah, so MetDesk is obviously a weather forecasting company. We have a focus on two kind of key areas, I guess. One is the energy markets, and the other is the transportation side of things. So we move a lot of trains and freight and all that kind of thing around Europe. In the energy space, we have a dedicated energy forecasting team. We produce a whole range of kind of energy specific weather forecast data. We support trade floors. We do a lot of renewable forecasting, offshore operations and maintenance. We also provide a fair amount of kind of climatology data. So, in the modern age where, there's lots of algorithmic trading systems and that kind of thing, there's always a big requirement for kind of what I call training data, and the sort of climatology side of our business does very well out of that kind of stuff. So we run a 365 days a year operation. It's 24/7 as well, headquartered in Buckinghamshire, and I'm pleased to say over the sort of 7-8 years that we've been operating, we've managed to gain the trust of most of the larger power generators and traders and that kind of thing that adopted across Europe and everything. So I just wanted to say, before I get into the kind of meat of the presentation, I'm going to focus on the wind side of the equation today, and what I'm going to basically do is look at where we've come from and where we're moving to. Again, like I say, I'm going to use wind as the main focus, but I think a lot of the improvements that are being made to the wind forecasting side of things, equally that can be made relevant to met ocean parameters and that kind of stuff as well. So look at this with your eyes wide open, and just be aware that there's lots and lots of improvements that I think we can be making to weather forecasting as we head towards sort of 2050 and everything. So I want to look at where we've come from initially. Model resolution is one of the big things for weather forecasting, and by that I mean how big are the grids that we're using to be able to make our predictions. Now the limiting factor here has always been computer processing. So as we've seen computers get bigger and faster, the size of weather grids and that kind of thing is reduced dramatically. So going back into the 70s, we'd have been operating with 210 kilometer global grids. These on the global models, they're now now operating at sort of 9 kilometers. So there's been a huge increase in weather resolution. Some of the local area grids, we've come down from 25 kilometers to 1.5 kilometers. Back in the olden days, we'd get 4 time periods a day from which to make our weather forecast. So a snapshot in time going out maybe 5 days into the future, every 6 hours. We'd only get 1 forecast update per day from the weather model providers. Very often it was a case of just looking at Met Office data. We didn't have access to ECMWF or the many local weather models and that kind of thing. So what there is now is a huge amount of weather models. Some are better than others, but just to kind of give you an understanding of where we were back in the 80s. I'm looking at these 210 kilometer grids here. This is the kind of stuff we'd be looking at in the noughties, 2010, that kind of thing. And you can see, what you can see, the physics was, pulling out, what we're looking at here is precipitation. So you've got precipitation wrapping around what would be a low pressure centre, probably centred somewhere over the north of Scotland there. Although it kind of, all of these different weather models will show, a similar broad picture. You can very much see that the definition is much better in the more recent weather models down here in the bottom right hand slide and everything. This particular image here is what I'd describe as being the sort of cutting edge of the forecast data that's available to us these days. So this is a 1.5 kilometer model provided by the Met Office. Now what you can see is, wind ramp events here. So you've got a wind ramp event sort of moving or sliding away towards the southeast over here. Very, very smooth flow. We're able to pick out, a far more sort of gusty nature of wind speed here. Far more turbulent airflow. Again, down here in the southwest, we've got, quite a nice smooth wind and everything. So, the ability as us as weather forecasters to make a better interpretation of what's happening in terms of different types of weather is improved enormously. So we have to still be careful with these kind of data sets, because although we still have an understanding of better types of weather, we're still in a position where I think there's errors in space and time that that make forecasting difficult. So although we can see this gusty weather in a little bit more detail here, it won't, the weather models won't actually tell us exactly when the wind gusts are coming through. So I'm very much expecting as these weather models evolve through time, that these weather models will start to improve on giving us a better time and space and magnitude forecast. So hopefully, the improvements to weather model resolutions are going to go in that direction. I think, looking at further improvements, we're going to be 5-10 years down the line. I think certainly some of the weather modelers will be, going sub 1 kilometre for input data sets. I'd certainly be expecting the weather modelers to be, producing more vertical levels, so a much better understanding of, how wind speeds are actually flowing through an array of turbines. There's things like low-level jets that we didn't have a huge amount of understanding. We didn't even know they were there before the offshore wind industry went into the North Sea and started putting turbines up. We're looking at SCADA data and seeing these, this weather phenomenon that nobody ever expected. So now we understand that those kind of phenomena are actually there. You can then get that back into the modelling process. Things like understanding the land and sea interaction. So how does the wind behave as it moves from the land to the sea? We're expecting, a lot more, intelligent physics to go into the models. And lastly, I think, we'd expect to see, more updates every day for some of these weather models. Some of the kind of weather models that are used in the US for, hurricane prediction and stuff like that, they're updating in on an hourly basis. So I think, ECMWF and the Met Office and companies like that, we'll certainly see them, improving the granularity of available data sets. Forecast skill has certainly improved. So what I'm looking at here is, forecast skill in 2009 compared to forecast skill in 2020. And you can see, the error at B+1 was around about 4 meters per second. Now we're looking at, just under 2 meters per second. B+10, big improvement there as well, 12 meters per second 10 years ago, 8.5 meters per second, now. So I'd expect to see, far more improvements on that side of things. I think, as kind of the private sector, where the businesses have come into this space, we see higher resolution data sets being provided. So what that means, taking data from the global or the local weather models and applying that specifically to, a wind farm or a solar asset or something like that. We have these very well established, forecast nesting processes and model blending, where we're taking the good bits out of Met Office data, we're taking the good bits out of ECMWF data and combining that to make a better forecast than, simply using one single source of weather data. But again, there's a word of warning there that, particularly when you're looking at embedding those kind of data sets into, a full array and trying to build, wake models and that kind of thing. You're only as good as the weather inputs that you're putting into that model. So I think as we move forwards, there'll be a greater use of using ensemble forecasting, which I'll come on to shortly as well, in creating scenarios. So rather than using kind of the deterministic approach, a single forecast value, looking at a range of forecast outputs or ensemble members to produce a more likely forecast. So probability forecasting, it's been around, 10, 15 years now. Like I say, traditionally, I think we've always used, a deterministic approach to forecasting, and there's been less of an understanding of risk. So we've been saying, the forecast for 2 days down the line at X point in the North Sea would be, 12 meters per second. Now we're far more comfortable, I think, with saying, this is what the forecast is, and this is the spread of outcomes that we could expect to see, bearing in mind that, weather forecasting, it's never been an exact science, and, we're putting more of a risk statement into the forecasting that we're doing. And I think, again, with the forecasting process, that that certainly MetDesk is envisaging. We're looking to evolve the ensemble forecasting process to use, things like machine learning and that kind of thing to be able to kind of shift the forecast in a more likely outcome. And I'm seeing, some of the work we're doing behind the scenes, I'm seeing enormous potential for improvement of forecasting, particularly in the sort of 4 to 15 day period there. It's probably worth saying that, the actual weather forecast providers as well, ECMWF and GFS, who we rely on a lot for the base data that goes into a lot of our kind of bespoke modelling processes, they very much have probabilistic forecasting at the heart of where they want to move their systems as well. So, we've seen recent movements from ECMWF, for example, to extend the forecast horizon. Traditionally, they'd go maybe 30 days out into the future. In the last 18 months or so, their ensemble forecasting system has now increased out to 46 days. In the next couple of weeks or so, the GFS, so the American forecasters, are doing a big upgrade to their ensemble forecasting systems. So there'll be an additional 10 members in their ensemble spread, and they'll be extending their forecast runs from 15 days out to 35 days into the future. So certainly we're seeing better certainty coming into the medium to longer term, and by that I mean the sort of 4 or 5 day period out to sort of anywhere up to a month and a half ahead. I think there's still a fair amount of work to be done on the short range ensemble. Nobody's yet really cracked a decent ensemble spread, for certainly not from a numerical weather forecasting point of view anyway, for day ahead or a couple of days ahead purposes. I think weather modelers can do more in that space, but again, I'm expecting improvements to be made on that side of things. Internally, within MetDesk, we use these kind of ensemble clustering techniques. They're certainly very popular with many of the energy traders that we have across Europe. The basic concept here is, rather than using the mean of the ensemble as the most likely forecast point, further down the forecast horizon, we look to see where there's similar forecast outputs, and then create like a clustered or output based on where we see a nice tight grouping in the forecast. So just using this example here for the UK, what we're seeing is the ensemble spread here. The grey line here represents a climate normal. So we see temperatures dropping off for a few days. Good consistency there between all forecast ensemble members. Then we see, around about the Monday point, we start to see, forecast data moving back towards, slightly more warmer temperatures. And then we see the spread really does start to increase around about the sort of 6 or 7 day mark. So, but within the actual spread of the ensemble, you can see there's a pretty good, tight grouping through this particular area here. So we're able to provide data sets these days which have a clustered approach to the ensemble forecast, which again is proved to be able to improve the the accuracy of forecasting. Obviously it won't always be right, but we're moving things in the right direction, certainly on the forecast clustering side of things. When we're looking at a kind of much longer range as well, I think we've used telecollections a lot in the past, and just to give a sort of brief understanding of what connections are, the basic principle there is kind of understanding how global weather patterns can influence the local detail. So we have, many of you will have come across things like El Nino, so ENSO. You might have come across the North Atlantic Oscillation, the Arctic Oscillation. You might have come across the polar vortex and southern stratospheric warming and all that kind of thing. In if you're on top of the weather, and all of these are their kind of big picture global phenomena that that tend to behave in a similar way. So when we have, let's say, for example, a positive NAO, we will have lots and lots of wet and windy weather in Northwest Europe. So we can use, pattern responders like the NAO to make, good quality, longer range predictions. We had a huge amount of success predicting the beast from the east from the 2018 winter by looking at SSW and polar vortex behaviour, which is basically the way the wind blows around the North Pole several kilometres up and everything. And by extrapolating, that information back down to the European scale and using some analogues from previous years, in certain instances, these teleconnections can give a far better understanding of what's going to happen further down the line than just looking at numerical weather forecast data and that kind of thing on a kind of standalone basis. So, I think there'll be a lot more understanding of these, these teleconnection processes. I think as we move forward, and these things are used enormously by the weather trading community and that kind of thing to kind of beat the market and get the pricing signals right for wholesale electricity and everything. So I think that will come to the fore a lot more. Just kind of moving the kind of thrust of the discussion away from models and modelling and that kind of thing. I think one of the big things that we've seen more recently is the development of weather APIs. So traditionally, the delivery of weather forecast data was very prescriptive from a lot of weather providers, and I think the locations were static, the available parameters were static. The weather forecast providers chose your time steps and forecast horizons and that kind of thing. Over the last 3 or 4 years, APIs have certainly come to the fore for weather forecast data, which basically puts it puts all of the weather data that we have as weather forecasters into the hands of, the power companies and, the data engineers and all that kind of stuff. So, the data is far more available now, and I think that lends itself then to a far greater level of sophistication in terms of some of the stuff that I think Ty was talking about previously, matching up weather data sets to, specific behaviour of wind farms and that kind of thing, and, failures of assets and that kind of thing. Having that, data at your fingertips and, being able to get that into machine learning processes very, very quickly is certainly something that's happening on the API side of things. So that kind of leads me to my next slide, and that's what we're also doing from our perspective on the weather forecasting side of things is, rather than trying to say to our customers, you've got a 3-hour weather forecast window here, we're taking data sets from specific examples of vessel turbine accessibility and stuff like that. So the question has very much gone away from, or the instruction has very much gone away from, you've got a 3-hour weather window to, you've got a 3-hour weather window today. Now, what are we going to do with it? What's the best use of that 3-hour time? Excuse me. So, that's definitely something that we've seen come to the fore more recently. I think another approach, this kind of comes down to, the smarter use of data. So it's looking at, how do we take data from nearby wind farms to better inform wind farms that are, upwind of one particular asset or another. So can we correct the forecast in the right direction if we already know what's happened as a wind ramp has come through a specific area? So it's all about making adjustments to space and time in terms of the forecast. And there's no doubt that, you know, the smarter use of data, you know, from wind farm to wind farm is improving weather forecast output. So I'm just show an example here of this is a wind forecast from, you know, raw model data, but if we're integrating you know, data from nearby wind farms, you know, we can see we're much closer to, you know, the wind ramp timings, and, you know, the errors are far less. But to a certain extent, this kind of forecasting, you know, relies on the pooling of data from, you know, sometimes different wind farms, different wind farm operators, and that kind of thing. I don't think there's quite enough data sharing that's going on in the marketplace right now. It would not be nice to get more data into our system so we could do more of this kind of stuff. But it's certainly this kind of, you know, where this kind of forecasting approach is being adopted in areas where there's densely populated wind turbines. You know, they do a lot of this kind of stuff in Germany. You know, Scotland, I'm seeing an increased amount of this kind of data, smart data usage as well. So, you know, it's certainly something that I'd encourage from our perspective. I think we have to be careful as well. You know, there's an image here which shows, you know, lots of the development areas and that kind of thing in the southern North Sea there. You know, we've seen studies in the last 18 months or so, which, you know, that is used LiDAR data to be, you know, to predict what the effect of one wind farm is on another wind farm that's just upwind of it. So, and there's no doubt that, you know, nearby wind farms will cannibalise the available wind resource and that kind of thing. So we have to be careful with, you know, the way the weather models work, because they don't take into account, you know, this cannibalisation approach. So specific modelling is required to, you know, to understand more about what the wind is actually doing in these areas. So yeah, we just need to be wary of that. And I think I'm just going to kind of close off with saying, you know, there's other things happening as well. You know, there's I'm seeing a lot of news in the press with floating wind. That's going to mean wind is going to go further offshore. We've learned a lot about, you know, what's happening in the North Sea in terms of weather forecast prediction and that kind of thing. But with everything moving further offshore with new generation technologies, you know, people are going to, if cogeneration is something that's going to happen, people are going to want decent wave resource coupled with decent wind resource and that kind of thing. So we'll have to adapt the approach that we take to forecasting there. And I think that the last thing, I think, you know, everything's moving into new territories as well. So we're seeing activity in the US, we're seeing activity in the Far East. You know, all of these different things, you know, come with some new challenges and everything. And, you know, that's where engagement with, you know, the likes of us in the weather forecasting community will no doubt help. So that's the end of my presentation. So I'll hand back to Steve now. If you've got any questions, far away.
Good, thanks, Jeremy. Some good discussion points there as well. And it is interesting to see how there is some correlations between what we've been talking earlier, just about AI and machine learning, and the use of all data sets in relation to improving the output for offshore wind. And again, we do sometimes forget, you know, on the basis that if you're not working in the met side of the business, that the wind resource is the biggest benefit for making offshore wind work, because without the wind, you don't have a business from that point. So getting it right is critical from that end. To that point, Jez, I've got a couple of questions here. So ramp effect, and I know you touched on that a couple of times in your presentation there. Obviously, it's got a big impact on sort of wind farms. Maybe worthwhile just explain to the non-Met people on the call just what a ramp effect is, Jeremy, as well, just from that point. But do you see that being overcome in the future, or is that something which it's just going to be there, you know, from that point?
Yeah, I mean, what we're trying to do is, you know, wind ramps. What we're talking about there is the wind speed going from, you know, a low level where you've got no generation to a high level of wind speed where you've got lots and lots of generation. Now, that can happen suddenly, it can happen gradually. Often, often what I see when I look at our power forecast is we will get the wind ramp absolutely bang on, but it might be offset by 3/4 of an hour because the weather models haven't quite captured the timing of the wind ramp as well as it could be. So again, a lot of this, getting those wind ramp right, and that's important for making sure that the grid is properly balanced and power traders are making the right trades at the right time and that kind of thing. But getting that forecast right, it all comes down to weather model resolution. Now, fortunately, over the last 18 months, 2 years or so, particularly with the ECMWF data sets, they've moved from a 3 hourly data sets down to 1 hourly data sets. So they've had higher granularity in some of the data. So that's allowed us to be able to capture these wind ramp events better. I don't think we're never going to get it absolutely bang on from a pure numerical weather forecasting perspective. But I think in the second to last slide that I showed you there, if you own the the wind farm at the back end of the array, and we know that that wind ramp is 3/4 of an hour out, as it's moving through several successive wind farms. If we were able to get data from all of those wind farms, by the time that wind gets to that third wind farm, we'll have a much better understanding of when that wind ramp will actually happen. So there are big improvements that are still there to be made and everything, but it relies on this kind of collaborative approach, I think. So it's, I think Ty mentioned a lot of this. It's really digging into the observation data from from anemometers and stuff like that, and making that data available that will improve the wind ramp equation there, I think.
That's a very good point. Another question here. Is the wind industry doing enough to ensure that offshore wind meteorology is moving in the right direction? And you talked about collaboration as well. As we're great proponents at the Catapult for collaboration across the sector. Are you seeing that from that point of view? Is the wind industry?
Yeah, it's pretty good, but I think I'm going to go back to my previous conversation. Lots of the conversations I have are very often with they'll be with one power producer, and then I'll have exactly the same set of discussions with another power producer. So it would be nice to see some of those guys coming together, I think, in a better way to be able to crack these kind of slightly more difficult weather forecasting conundrums. So rather than doing it on an individual company by company basis, get people from different companies coming together and kind of thrashing it out themselves, I think.
Yeah, indeed, and I think that's as much as that feedback you're getting from an O&M perspective, certainly from the owner operators, to sort of get that as much as it fits back to the trading, which always seems to be a bit of a disconnect somewhere along the line, I think.
Yeah.
Another question: is there still space for human intervention in weather forecasting, or do you envisage all predictions to be done by the machine and like that in years to come?
Yeah, I very much hope there's always a place for the weather forecaster within the equation. But I think the role of the weather forecaster will probably change. I mean, going back 15 or 20 years, I think it was quite easy to second guess the models and try and it was easy to see where they had issues and that perhaps they weren't as good as they could be. And I think as the weather models have improved, the granularity's got better, the resolution has got better. It's become more and more difficult to have produce a better forecast from a human being perspective. But that said, I mean, I touched on teleconnections there. Certainly, when the beast from the east was coming into the forecast horizon in 2018, the human being weather forecasters beat the numerical weather forecast prediction, you know, the likes of ECMWF and the Met Office, you know, medium to long range forecasts. They beat them hands down in instances like that. So, you know, I touched on teleconnections and, you know, these kind of bigger picture global phenomenon. That's where I think the, you know, the true skill of the weather forecaster will come to the fore over the next sort of 10, 20 years or so, is by looking for other teleconnections and trying to be cleverer with, you know, analog data and, you know, historical weather forecast information, and trying to put more of these teleconnection processes into place. And now some of that can be done by machine learning, of course, but there's still going to be a place for the human being, I think.
Indeed, indeed. And a prediction for you at the end: where do you see the largest improvements to weather forecasting in the next 10 years? Short, medium, or long range?
I think it will be the longer range, to be honest. I think that's still the big, you know, the most difficult thing to do, I think, is the you know, predict what the atmosphere is doing, you know, 3, 4, 5 months down the line and everything. But again, that all relates back to teleconnections. We see, you know, in a warming world where we see, you know, far less sea ice across the poles and stuff like that, we've certainly seen an atmospheric behavioural change. So what a lot of our forecasters see now, I think, is once we get stuck into a certain weather regime, it will often be more intense and longer lived. So we look at, you know, the very, very wet and windy weather we had you know, through the course of December, January and February this year. Then there was, you know, that was a long-term you know, wet and windy regime. Then we went, as lockdown came to the fore, you know, most of Northwest Europe went into this amazing 6 or 7 weeks of, you know, barely seeing a cloud in the sky and everything. So the predictability of that kind of stuff is, I think we're going to be able to predict those kind of you know, weather phenomenon with a bit more accuracy as we go further into the future, I think.
Yeah, indeed. Thanks, Jeremy. I've got no more questions from this end, but please do stick around for the final sort of session. And I'm sure that there will be more questions and interest coming off of this group as we go on. So thank you again, Jeremy, for your presentation. Our final speaker today is a guy called Joshua Greenslade. Josh works for Onyx Insight in Nottingham. And from his bio, which I'm reading here, Josh did his master's degree in physics at University of Nottingham before moving into a PhD at Imperial, where he studied astrophysics. So basically, he is a rocket scientist. There's no doubt about that. During this time, a lot of time involved with advanced statistical analysis on cosmological data sets, communicating with the general public about the numerous ways the universe might end. There we go. It's an interesting discussion point. And 3D printing of planets as a side gig. I like that. After a brief stint as a postdoc at Imperial, he is now very much a senior member of the ML team at Onyx Insight, an engineering company specialized in predictive maintenance for wind farms. So, Joshua, I'll hand over to you to discuss how predictive maintenance can actually work for an O&M environment.
Thanks very much, Steve. First off, can everyone hear me and can everyone see my screen?
All good, yeah.
All good, fantastic. Right, so yeah, my name's Dr. Joshua Greenslade. I just want to begin by really thanking the other panelists and presenters today. I think one thing that's become really clear to me is we're in a period of really rapid change in the wind industry, and it's quite exciting to see and think about where we might be in 5 years' time. in some aspects, it's a bit worrying as well, because I think my kind of slide of the session has to go to Ty's slide, where he showed the number of companies who thought they were kind of going to be ready for the kind of digital future. And then when Ty's company talked to them, Cognitive talked to them, they found they really weren't. And I suspect that might be a theme we see going forward in the next 5 years. As Steve says, I work for a company called Onyx Insights. Onyx Insights generally provide predictive maintenance and advanced analytics across the world. We have 10+ years experience in engineering around rotatory machinery design, monitoring and lubrication. So we're not just a data science startup, we are an engineering company who happens to do data science rather than a data science company who happen to do engineering. And this is really underpinned by our track record around what we've been monitoring. So I think these numbers are out of date. I think we're now monitoring 6,000+ wind turbines, both onshore and offshore. We've done 2,000 gearbox inspections, 3.4 gigawatts of installed offshore wind turbine types covered. All of this generally is trying to be me convincing you that we generally know what we're doing when it comes to wind turbines and wind turbines engineering. Because this talk is generally not going to be in too much detail about wind turbines specifically. Rather, at the end of the day, I thought I'd give a nice, very high-level talk about what machine learning actually is. Because I think the term machine learning has become a bit of a buzzword in common parlance. It's become a phrase that people throw out when they almost don't necessarily know what they mean, because machine learning has a very specific terminology and a very specific usage. It's things like, other terms are like blockchain or like cloud computing. They get thrown out quite a lot to display this kind of idea that you're in the next generation and you're getting ready, but often they're thrown out without much good reason behind them. So in the first half of this talk, I really want to go through and give everyone listening to this talk a really critical understanding of what the phrase machine learning actually means. So that if you hear it in the future, say some company says, we're using machine learning to achieve task X, you personally can then critically think about that statement and decide, does that sound sensible? In the second half of this talk, then I'll go into a bit more about how we can actually use that definition of machine learning and use machine learning to reduce O&M costs and get some really actionable insights on wind turbines specifically. It's a very high level talk though, there's very little maths involved, so it should be a nice end to the session. Now, as Steve points out, I kind of come from an academic perspective. So when I first encountered machine learning, it was very much in a theoretical and a academic environment. So it was all around the technical side of things. So I didn't really have a good understanding of how the world sees machine learning. What does kind of someone on the street think about machine learning if you ask them the question? So what I did is I did what any sensible person does in these circumstances, and I went to Google. And into Google, I typed in, can machine learning and will AI, and I simply let Google autocomplete for me the rest of the sentence, because I wanted to kind of get to know, well, what does the world think about machine learning and what does the world think about AI? And these are the results that it gave back to me. It gave back results like, can machine learning cure cancer? Can machine learning predict the lottery? Will AI take my job? Will the AI cause World War III? And I genuinely think, as someone who's interested in AI and machine learning, this is a fascinating data set. Just an idea of kind of what common things are people typing into Google around machine learning and AI. And from this, I kind of take away 3 key facts. Number 1, it's really clear that people are really excited and interested in applying machine learning to whatever they've got interest in. Whether that be someone in the wind industry saying, hey, we should apply machine learning to our data sets, or the lawyers sitting in their law firm saying, hey, how can we apply machine learning to what we're doing? Some of these terms, however, make it really clear that people generally don't have a good understanding of what machine learning actually is, what it can do, and particularly what its limitations are. It feels a bit at the moment like machine learning and AI is the new Christmas toy that everyone wants at Christmas, but no one's quite sure how to kind of use it correctly yet. And the third takeaway that I get, which I'm not going to talk about too much, but 100% should be considered, is people are concerned about the impact of machine learning on their personal and professional lives. I think that last question to Jeremy about are humans generally still have a place in predicting the weather? Will they still have a place, or will it all be machines? That's a manifestation of question number 3 there. A lot of people are concerned about what impact machine learning is going to have globally. But so I've talked again, I've used the phrase machine learning myself here a lot. And I promise you, I will be getting to a good definition of machine learning that you can take away and you can use in your lives and in your companies. But before I get to that definition, I need to clear up a few terms and things. So it's worth spending a tiny bit of time talking about what machines and computers have traditionally been good at doing and what humans have traditionally been good at doing, and mainly the difference between them. And I bring this up now because in the next set of slides, I'm going to show you a series of about 8 or 9 pictures. And for now, I just want you to consciously note down which picture or pictures do you notice first? Which pictures does your brain instantly lock onto? Because that will become relevant and important in a few seconds. So here is my slide showing kind of the differences between machines and humans. Machines traditionally have worked with simple mathematical operations and mathematical structures, things like big arrays of numbers, things like simple shapes like circles and squares, simple logic flows and multiplication, addition, all of these kind of simple mathematical structures. These are things that machines have traditionally been really good at working with. And for this reason, industries where those kind of mathematical structures, those simple mathematical structures dominate, those have been dominated by machines already for several decades. Think, for instance, about the finance industry, right? The finance industry has been dominated by computers and machines already for the past probably near 50 years. However, when it comes to more complex items like humans or landscapes or cities or lions, this is more where humans have dominated because humans are very good at pattern recognition. Again, thinking a bit about Jeremy's talk here, a lot of kind of what the Met Office do isn't necessarily simple mathematical operations. It's more noticing patterns in the weather. And that's potentially how machine learning can help. And that's also why I suspect that most of you, when I first moved on to this slide, you either saw this lion first or you saw this human first. That was where your brain went. That is no coincidence. It's because your brain has evolved to be able to detect those patterns and prioritize them, right? Your ancestors, when you evolved, if your ancestors were good at detecting the lion pattern or an angry human pattern, those were the ancestors that tended to survive and move on. Traditionally, however, machines have been really, really poor at detecting these kind of patterns. And it's only really with the advent of machine learning and in the last few years that machines have even started to be able to detect these kind of things. And that's very understandable because how do you write down the equation of a lion? There's no simple mathematical formula for a lion or structure. So you need something that's a bit more abstract, a bit more pattern-based to be able to do that. And finally, I can kind of move on now a bit to what my definition of machine learning generally is. And in the lead up to that, I just want to kind of complain a bit that machine learning has very, very poor PR. Most typical machine learning or data science talks I see, certainly on a technical level, look something a bit like this. They've got this big array of various tools that all these data scientists use and various platforms they use. And then they might move on and talk about which specific tools and which particular flavor of the algorithms they like to use. And then they might talk about the decision processes that went into how they went to decide whether to use k-means clustering or whether to use neural networks or whether to use naive Bayes. And then if you're very lucky, they might even talk about how the specific algorithm works and the flowchart of how decisions are made within that algorithm. And all of this is just way, way too much information. Because fundamentally, that is all machine learning is doing. And this is my definition for machine learning. And if you take nothing else away from my talk today, just remember this definition here and apply it whenever you hear someone talking about machine learning. Machine learning is a suite of tools and algorithms that enable computers to do pattern recognition. It's nothing more than that. It's nothing less than that. If you come across a company and they say they're doing machine learning, think, does that make sense to you? Is there some kind of pattern there that you suspect they can use in order to achieve their goal? If there isn't a pattern, or even a kind of, even if it's not obviously there, if there isn't even kind of any remote pattern you expect them to see, walk away from that company, because they're probably trying to pull the wool over your eyes. And we can go further here, because we can use this definition to really inform ourselves about when and where you should be using machine learning and how to get the most value out of it. So here are my kind of 3, I guess, golden rules for doing machine learning. And they're not the only 3 rules you should be aware of, but they're 3 rules that if you use them, you're going to get off to a pretty good start. Rule number 1, you cannot predict the lottery by rolling dice. Tomorrow, I could start a rival company to Jeremy's where I say, I'm going to predict the weather. And I'm going to do that by rolling a single dice. And if I get a 4 or 5 or a 6, then it's going to rain tomorrow. If I get a 1, a 2, or a 3, it's going to be sunny tomorrow. And eventually, if I roll that dice enough times, I might get a string of 7 days in a row where that dice has correctly predicted what the weather's going to be that day. Does that mean my dice is able to predict the weather? Of course not. It's a complete coincidence. But with the kind of data set sizes we're seeing today, those coincidences happen a lot. You can imagine that's very unlikely to happen if I just rolled a single dice. But what if I rolled 10,000 dice every single day and I just kind of picked one of those dice out? I guarantee you at least one of those dice is going to be able to predict the weather probably 30 times in a row. You need to be able to use your domain expertise and your engineering knowledge to think carefully about, is the pattern that I'm seeing a coincidence, or is it a reflection of the true underlying structure of the problem I'm trying to solve? The second key rule I really want you to be aware of here is not all data are created equal. And this is very similar to the first rule. If you are going to do machine learning and you have a goal you want to solve, you really need to be getting the right data in order to solve that goal. That data that you're getting has to have some kind of link to the problem you're trying to solve. You can't simply, for instance, I can't necessarily solve, I can't solve faults with wind turbines by, I don't know, monitoring what time I have dinner at home. Again, those 2 things might correlate with each other, but the idea that one is informing or causally related to the other is less, that's less certain. You need to be collecting data that are relevant to the problem you're trying to solve, as relevant as possible. And question number 3, or rule number 3, is it's really important to ask the right questions. I see a lot of companies saying something along the lines of, we've got all this data, we want to use machine learning on it. And I often ask them to do what? What do you want to do with it? And they're not sure. They're not sure why they want to use machine learning. They don't have a good question they want to answer. But as I said, machine learning is just a way of doing pattern recognition. If you don't have a good question that you want answered, and if you can't frame that question in such a way that it can be described mathematically, you're very unlikely to be able to get good results out of that model. It reminds me very much of the old phrase, the garbage in, garbage out. The exact same is true of machine learning. Be as strict as you can with your question and you will get better results out of it. So, armed with that definition, we can kind of move on a bit into how we might be able to use machine learning in order to get value out of wind turbines, or use machine learning on some of the data we have for the wind turbine sector. So how can we use machine learning for predictive maintenance, or more specifically, what patterns exist in our wind turbine data that might indicate faults or damage? And this is what I want to do in this section. And again, I'm going to build with you here today a really simple machine learning model, and we're going to see what we can do with these simple tools. Up here, I've got a plot of the temperature of a high-speed shaft bearing. Each different line represents a different turbine. The x-axis represents time, and the different colors represent whether that turbine failed during this time period, or sorry, whether that bearing had a fault in that time period or not. Specifically, the blue lines represent all the turbines that didn't, all the bearings that didn't have a fault, and the red lines represent all the bearings that did have a fault. The black line just simply shows the farm mean in this case. And this is taken from SCADA data, and SCADA data is often used as the kind of the first place to look when you're expecting to detect faults. But as you can see from this plot here, the turbines with faults and the turbines without faults are really indistinguishable from one another. In fact, there's about a 5 to 10 degree spread in between different turbines. So you'd have to wait until your bearing in your turbine gets 5 to 10 degrees hotter than it normally is before you'd be able to detect this normally. So the question is, can we use this data stream in a smarter way? Is there a pattern we can see? Well, let's take an individual bearing temperature. And let's say we want to build a machine learning model that predicts the temperature of this bearing using only other SCADA tags. Specifically, I'm going to train my model using this period of time here, the first 6 months from 2013. And then what temperature should our model predict? If it was going to be a reasonably accurate model, what temperature should we predict with no other information? Well, the simplest thing we can do is we can say, well, what's the mean temperature during that period of time? And we say the mean temperature is about 62.8 degrees. And congratulations, you've now built your first machine learning model. That's as simple as it is. But we think we can also do better. So let's bring in the generator RPM into this model and see if we can add some multiple of the generator RPM to this model to get a better model. And it turns out we can. It turns out if we add approximately 4007.9 times the generator RPM, we get this nice purple line here. And we can do better than that. We can start adding in other SCADA tags which might be relevant. We can, for instance, add in a certain multiple of the gear oil temperature. Or we can go further and add in about a certain multiple of the ambient temperature. And at this point, we've actually got a model, this purple line, which is pretty accurately modeling what the true bearing of the temperature is. And again, this is a simple machine learning model, but this is all it is. It's just being able to detect this pattern and effectively reproduce it. The question we have now is, what can we do with this model? And the next kind of 4 or 5 slides, and the last 4 or 5 slides of my talk, we're going to show you some of the things you can do with these kind of models in order to preempt faults with your turbines. So here I have a main bearing temperature. So this is temperature on the y-axis, time on the x-axis. In blue, I'm going to plot up the kind of measured temperature of that main bearing. And I want you to try and spot where the fault occurred during this time period, because there was a fault that occurred during this time period. This one, it's fairly easy to see that around late 2015, we see a sudden jump up in temperature, and indeed, that's where the fault is. If I now plot up what our very simple machine learning model predicted here, you can see this is what's plotted up in the green line. That's the predicted temperature. You can see there's suddenly a big difference once the fault occurs between the predicted temperature and the measured temperature. On this bottom chart just here, I'm just going to plot the difference between the measured and predicted temperatures here. So this is a bit easier to work with. It's effectively the residual. And as you can see, it very obviously kicks up quite highly in late 2015. Now, this isn't necessarily too impressive because you can kind of see by eye already that this is something going wrong. And you could almost have a static alarm threshold at around 50 degrees to detect this. So let's move on to example number 2. Example number 2, once again, there is a main bearing fault somewhere here. Can you tell where in this time period the main bearing fault took place? Now on this one, it's a bit more difficult because the temperature of the bearing doesn't really increase beyond its normal levels. So any static alarm thresholds wouldn't have been able to detect this. However, applying our machine learning model, we see that the difference between what's predicted and what's measured is maximized in around 2014, early 2014. And again, we would be able to detect this a lot easier using machine learning models and be able to take predictive or corrective maintenance rather than relying on reactive maintenance in this case. And we can go further. We're not just limited to main bearing examples. Here is an example of a high-speed shaft. There was a repair done at some point during this time period. Again, can you try and guess or see where it is? I'm going to say you probably can't, because once I put up even the model predictions, you'll see the model predictions are very, very closely following what the true temperature was. But if we look down at the residual, we can see a really obvious case in mid-2016 where the repair took place. And you'll notice on the y-axis here, I'm only talking about differences of 1 to 2 to 3 degrees. So a 3 to 5% change in the temperature is readily detectable by these kind of machine learning models. And this is where you can start to get some ideas about how you can use machine learning to really aid in predictive maintenance and be able to detect faults in components before they become critical or before they fail. The final example I want to show is another example of a main bearing. Again, there's no real obvious place where the fault might have taken place, but if we then apply our machine learning model to it, we can see that since around mid-2015, the temperature of this main bearing has been slowly increasing, only by 4 or 5 degrees. Again, we're only looking at about an 8 to 10% change in the temperature, but it becomes very obvious when you can compare what the temperature should be to what the temperature actually is. In this case, in fact, we use this method to figure out whether this was a problem with the main bearing or a problem with the planetary gears, because we also had a vibration system installed on this particular turbine. And if you read this box here, the vibration system couldn't tell if it was a problem with the main bearing or if it was a problem with the planetary gears. The two frequencies of vibration were very similar. So we were able to use this extra information to really distinguish between different fault origins. So summing up, I'm a tiny bit over time, I think, in terms of my 20 minutes, so I can sum up quite quickly. Generally, anywhere there's some kind of pattern, you know machine learning can potentially help. And again, I really want you to remember that definition from my talk, if you forget everything else, that all machine learning is a suite of tools and algorithms to do pattern recognition. And secondly, one thing you should be doing if you are thinking about using machine learning, have a goal and have a good understanding of what your problem is before you start. Because if you don't have that, if you just have a desire to use machine learning or use AI, you are probably not going to get good value out of it. So that's kind of the end of my talk. Very happy to take any questions, and thanks very much.
Thank you, Josh. Really good and entertaining sort of approach to understanding machine learning there. I must admit, I've sat through many sort of presentations in the early days about what machine learning is, and that was probably the most entertaining one I've come across, so thank you for that. I do have a couple of questions here, and interesting one straight off the bat here. The UK government used algorithms or machine learning for exam results to cataclysmic sort of results in the last couple of months. Do you think that there could be some form of backlash back in across industry just about the effectiveness of machine learning as a direct result of that?
Oh, I could talk on this one for 20 minutes, but I'll be quiet. So there's 2 points I want to make here. Point number one I want to make is they're entirely right. There was a huge backlash, but interestingly, the algorithm that Offshore used performed exactly to their expectations. It did the exact job they asked it to do. And this links back to my point about, I've got to go a bit far back here, but it links back to my point about you've got to ask the right question. Because the question they asked at Offshore was, how do we make a model that gives us a globally fair but consistent results with last year? And that is exactly what the model did. On a global scale or on a UK-wide scale, the results were fair and the results were consistent with last year. The problem with that model is they didn't take into account the fact that it's not a locally fair model. It was incredibly biased against local results and incredibly unfair on a local and personal level, which is entirely right that they, in that sense, kind of maybe thought again about how did they, whether they should have reversed the results or not. And I'm not getting into that, but 100%, this is an exact example of they asked a question and they got an answer. Whether that was the right question to ask or not is something different. And it shows the importance of being really careful about asking the right questions when you're using machine learning. And the exact same thing can happen in wind turbines as well.
Yeah, and I think that's absolutely right, and it fits very much strongly back to the data maturity points that Tom was bringing up in his presentation about, if you don't get to a point whereby you're using machine learning effectively and properly, you will get complete and utter disasters like the government actually managed to produce and upsetting many sort of kids around the country. Okay, thanks for that. Do sensor calibration or the lack of alter the results you get? That's a good question.
Yeah, often. Ty touched on this quite a lot, I think, in his talk around data maturity and the preparedness of companies about how ready they are to perform machine learning, because you're fundamentally often relying on the fact that you believe your data is good. And it is sad to say, but it is often in the wind industry that it is not good, whether it's because companies don't take enough care to calibrate their sensors when they're first installed, or don't take enough care to put sensors back in the right places during maintenance. I have once had a company who accidentally put their nacelle temperature sensor directly on an exhaust vent for the generator cooling system.
Right.
And again, you're not going to be able to convince anyone to go back up a tower and move just a single sensor, especially not if you're offshore. So there needs to be a lot more care about how you collect this data and how you present it. Even in this instance here, where I'm just showing differences between high-speed shaft bearing temperatures, many of these can just be calibration errors. And you can see we can make models which are accurate down to the, 3 to 5% level and below. I'm sure Ty has models he's saying where he can get down to kind of the 1% level as well. But if your calibration accuracy is uncertain by 6, 7, 8%, then you're never going to be able to get accurate numbers. Your uncertainty, the uncertainty Jeremy was talking about, that's always going to be much bigger than the results you can actually get. So we can detect this. We often do detect sensor faults, and they're quite easy to pick up a lot of the time. But ensuring the initial calibration is done correctly can be a big problem. And again, it just affects the uncertainty more than anything else. Gives it almost a lower limit that you can't get past.
Yeah, indeed. I'm going to pull in Jeremy and Ty because we've got about 10, 15 minutes left, just to sort of, if you guys could put your cameras on and your mics on, that'd be great. Thank you. And then we can just go through the next questions. And I've got a good one here, which is, where does the industry, and let's just talk about the wind industry, both on and offshore, because that kind of makes sense from that perspective. Where is the industry heading in terms of machine learning? And I'll give that to Ty to start with, as he's been making a nice cup of tea, no doubt, since we left.
I think people are catching up to what Josh is talking about now. I think that's probably the current direction. It's generally referred to as APR, Advanced Pattern Recognition Solutions. People are trying to, because they've got lots. This is a key and important point, actually, and it relates back to what Josh was saying. People have got lots of SCADA data. It's not big data in the way that a lot of people think it is. In fact, the way that Josh talks about it is where it's big. So they're seeing and really starting to dig into that. I think between a few companies back in the day when the first advanced pattern recognition systems were coming out, it was very hard to provide value cases. In essence, the beginning of my career when I invented solutions in that space was all about providing value cases, and it changes as you go from technology to technology, so from conventional power into wind, and seeing the value case development over the last decade plus, it's beginning to get to a point where people are just recognizing, yes, we should have a vibration analysis and it should be live. We should, or close to real time. We should have APR systems against our SCADA data, specifically in offshore wind because of the additional value case. I think, that's really with machine learning, that's where most companies are going to get to that point. I think a lot of people think they're at that point and they really aren't. But I think the combination, and this is really interesting actually, the combination that Josh showed of APR with the vibration solution, for me, and then the step into the really tiny data, which is the failure data, because there really isn't a lot of that, and how you start bringing those relationships together, that's really exciting. And incorporating the knowledge and intelligence of real people who did real work, engineering, science, whatever it was, that observation data, and feeding that back into solutions. That's how we're going to push towards, the red eye AI, towards the AI solution, and away from the kind of Terminator style future that people see of AI, and what the reality of that should be. It's very much as Josh started out with the kind of Google analogy. We often, when we describe or talk about AI, or machine learning, we say, well, the first place to go and look is Google, because just the way Google works is how everything should really work. So I'm sure, like the other guys, I could probably talk about this for a long time. So
indeed. And I'm conscious of time as well. So as we're sort of coming towards the end of today's session, I would just like to talk about, and the same question for all three of you, because the impacts are just as relative, if not from a different perspective. So the question I would like to pose to the three of you is, what has the sector got to do to embrace AI and machine learning and the use of data much more effectively than it is currently doing? Let's start with you, Jez, on the end there.
Yeah, I mean, it's making that data available a lot of the time. I mean, Steve, you'll remember discussions that we had maybe 10 years ago about, weather forecasting. Yeah, when I look at weather forecasting, it's been, if you take Josh's definition of machine learning, we've been doing that kind of stuff for 25 years, 30 years or so, when we look at MOS forecasting and stuff like that. So it's getting to the data that you actually require, I think, in order to make improvements to weather data sets and stuff. So it's, as weather forecasters, we're always hungry for that data. We can, particularly where you've got, difficult sites that might be close to the coast and stuff like that, the output from the weather, the numerical weather forecasters, it's almost not difficult to fit into the holes. You're trying to put square pegs into round holes to get the forecast out and everything like that. And it's opening up those data sets and everything that is absolutely crucial to us being able to get the outcomes that we want to provide and everything. So it's the same old stories. We've had that discussion a zillion times probably. It's make the data available to us and we'll get it into a usable format that will give you an edge on whatever task it is that you're trying to do, or whatever forecast you're trying to improve upon. And I think there's often a lot of tidying up. Both of the other guys have talked about this. I can't stress enough the value of keeping your data sets nice and tidy and clean and stuff like that, because the biggest headaches I think that we have is when we're going through all of this kind of data, it's pulling out the dodgy bits and the bits that haven't been looked after properly. That's what takes the vast majority of the time. You've got to do that before you can start to make decent relationships and everything. So it's one, making the data available, and number two is keep it as clean as you can. I know that's a difficult thing to do because lots of people are collecting lots and lots of data, but that would be my advice, I think.
Okay, Josh, same question to you. What has the sector got to do in relation to embracing digital and data more effectively?
I think Jeremy's really hit the nail on the head here in terms of the data quality in the wind industry is good at best. Is the kind way of putting it. And he's correct very much when he says quite a lot of time is spent going through this data and cleaning it up for other people. He kind of talks a bit about, and he's right, like a lot of people don't share their data and they sit on it as if as if it's, there's the analogy, right? There's the analogy that data is the new oil. And I think this analogy is more right than people think. And that's because like crude oil, like raw oil, raw data is useless to you. It's absolutely useless to you until you process it, until you refine it. And you've got a lot of companies, I think, who sit on their raw data and say, no, we don't want to give this out to anyone. We don't want to put this anywhere because we can make money off this. And I kind of sit there with my head in my hand sometimes thinking, no, you're not. You're just sitting there on a lot of storage capacity. Another thing that I think is very useful, there's two other points I kind of want to add to Jeremy's point here. Number one is not just about kind of be clean with your data, but be consistent in how you store it. A lot of the time, we don't particularly care if your data's bad or in a weird state. You know, we can kind of clean it. Anyone in kind of mine or Ty's or Jeremy's position has probably spent countless hours cleaning data sets, where you're very good at doing that. What's a lot more difficult to do it is where 1 year the data set is in this format, and then someone comes along and changes it, and then someone comes along and changes some names, and then someone comes along and changes something else. Because then we've got to do our job 4 or 5 times in a row, and it's often incredibly difficult to automate a process where the underlying data structure is changing every 6 months. And the second point I guess I want to raise around this, and Ty's already touched on this point slightly, capture your failure data. There are so many people I know and so many companies I know where they capture their failure data by writing it down in a notebook on site, and that's it. Or, you know, they've got a single CSV file that's sent around to 3 or 4 people and then end up duplicated. But that kind of information, this small data that Ty was talking about, that's some of the gold dust. With that information, you can do so much more with the big data you've also got sitting there. But if you don't capture that data sensibly or ideally automatically, that just gets lost to the wind very, very easily.
Totally agree with that. Indeed, small data needs to rule, basically, at the end of the day, doesn't it? Ty, last word from you on the subject of the data mature, the sector becoming more mature.
Absolutely echoing what the guys have said. People don't get this, and I'm going to use the word vector. I know it's a bit scary for some people, but in order to make all of this stuff work, the way you collect and keep your data is really, really important. Time synchronicity is a big deal, keeping things in a way that enables you to be able to compare information from one system to another. You know, these are the things that get us to the next step, the next stage, and enable us, in essence, to build solutions that can do a lot of this cleaning and identification of the nonsense first to get us through to that kind of pure outcome that can then be used for real things. And that's the only way that we can drive action, and collecting data is absolutely pointless if you're not going to drive action, because that's where the value comes from. The whole game here is to produce more energy and to drive down the cost of energy. You know, that's what we're trying to do. And the only way we can do that is by taking action. And that really is the goal for all of it. Excellent.
Good points. Thank you, gentlemen, for all of your time and your presentations today, and your comment has been really, really beneficial and quite good to get an insight from 3 very different parts of the industry from there. So thank you for that. We were bang on time, which means that Vicky will be very happy, the coordinator of today. And I'll now hand you over to Ben George, who's the operations manager for Grimsby.
Thanks, Steve, and thanks very much everybody involved in that discussion. That was really fascinating. Well, I think everybody's learned a lot today. It's been really, really fantastic, the things that have come out. So that's brilliant. I'm just going to share my screen. I promise I'm only going to take 2 minutes of your time before everybody can disappear to bar o'clock. Right. Okay, so there were, I think there were a number of takeaways that we can really pull out there today. So the first bit with the introduction by myself and Catherine. So we're really, the OMCE is really about trying to give that thematic and physical focus to O&M. Now we have been talking a lot today about the cutting edge technology, but that's not everything. Okay, so there are also today's O&M issues that might just require a slide rule to fix. So we're also involved in those. All right, the inspection, maintenance and repair. So when we were looking at that today, we were specifically focusing on the robotics and autonomous systems. Dan Sumner was leading that discussion. Fantastic presentations from all of the participants today. The big things that I got out of that is that there are massive benefits of or with integration of live and virtual, and the human factors matter. So the pink fleshy bits and how they relate to the machines, really, really important, and we need to get that right, otherwise they just won't take. For the O&M decarbonisation, which today was focused specifically on clean maritime with Stu Barnes, there's a lot of industry pull and there's great opportunity for the UK in that. And there's also, as we heard today, a huge amount of activity that's already started through a bunch of the companies that were involved. What it does need is some government support and cross-sector collaboration to make sure that we energise, so what we did there, and accelerate that transition. Really important piece. We just finished with next-gen ops and control, and specifically focusing on the data and digital side of that with Steve and crew. So what did I take away from that? Well, most companies are not getting what they could from their data, so they're not as data mature as they think they are. Data resolution and predictions are rapidly improving, with the service offerings constantly evolving and being tailored to the end user, really important. And I think a takeaway that we can all use for our daily lives, getting value means asking the right question. So all that remains for me to say is thank you very much for everybody, the audience and the viewers at home. Thank you very much to all the speakers, a stellar list. Did a fantastic job there today, and all of the information that has been presented today will be available on our website. The appropriate links will be emailed to everybody that participated today in a follow-up email, so look out for that. All that remains is to say thank you to everybody, and obviously thank you to Vicky, who's been working very hard behind the scenes to make sure that the event worked today, and we'd like to see you at the OMCE soon. Thanks very much. And that's it. Thanks, Vicky.